device. There was a full portfolio of solutions to allow you to access the same data on your mobile phone and your laptop from anywhere that you ever worked, the same data securely, the same application, the same collaboration tools. So one of these products is Xen Server. It is a server virtualization product. It can be used as standalone or as a platform for other Citrix products such as NetScaler and Xen Desktop and many others. Xen Server is based on Xen. So Xen is it's an open source hypervisor. Citrix moved development of Xen into a separate foundation, a separate project based on Linux Foundation collaborative project in April 2013. And later the same year, ARM joined the Xen Project Advisory Board. So now Xen an official Linux Foundation collaborative project. So what is Xen more in details? So Xen is a very small, so less than 100,000 lines of code hypervisor, GPL-v2 licensed, like the Linux kernel, and is particularly popular in the cloud. Amazon has, is EC2, is entirely based on Xen. Rackspace and Linode are also based on Xen. So most of the largest public cloud today are based on the Xen hypervisor. So Xen is a type 1, so the architecture is a bit different. Xen runs directly on the hardware. Everything else in the system are just virtual machines, including DOM0, that is a privileged virtual machine that runs the device driver for the hardware. It also runs the backends, the paravirtualized backends, to share these hardware resources with the other VMs, such as network card, network and disk, console, and so on. So typically, DOM0 runs the driver for things like the SATA controller, your NICs, and then it shares them with the other DOMUs through these paravirtualized protocols. The front end in the other guest are driver, typically in your OS kernel, like Linux. And this driver create a corresponding virtual device in your guest, so a virtual console device, a virtual network card, a virtual disk, and so on. But there is no reason why you should put all your drivers and all your paravirtualized backends in DOM0. It's actually pretty easy to split them up. You can, for example, move the network driver into a separate domain, assign the network card to it. So now we have what we call a network driver domain, run the paravirtualized network backend in this domain. Now the entirety of the network stack is isolated from the rest of the system. So this is good, obviously, for isolation, because now a bug in the network driver, it can't bring down the entire system, can at most bring down the network driver domain and the connectivity on your host, but that's it. You can reboot the network driver domain, and everything stays online, including the network. As soon as it's back, of course, with a small blip. So it's good for resilience. It's good for security because now the network stack is running in unprivileged mode. So even if somebody managed to break into the network driver domain, from there it cannot actually go anywhere. So yeah, so everything I said so far these are advantages of the Xen architecture that are used in several products based on Xen today. They're true on x86, but they're also true on ARM. What is more interesting is that I believe that actually Xen on ARM is better than Xen on x86. The reason is that when we started the project, we didn't just do a straight port of Xen to the ARM architecture. We actually took the opportunity to re-architect Xen, to improve it, to remove the crap that we accumulated over the many years of x86 development. So first and foremost, we don't do any emulation. So Xen on ARM does not do any emulation at all. There are no emulated interfaces. We have no QEMU running. So why do we do that? So first of all, emulation is low, right? So running anything in emulation is low. Second of all, emulated interfaces tend to be larger than paravirtualized interfaces. A larger interface means a larger surface of attack. A larger surface of attack, it means more opportunity for a hacker to break into your system. So emulated interfaces not only are slower, but are also less secure. So I'm really proud to say that we managed to get rid of all of them in Xen on ARM. The other big improvement is, I don't know how familiar you are with Xenon x86, but there are two main kind of guests. One is called PV guest, and this is what you typically use when you get a Linux instance on Amazon. And another one is HVM guest, that is what you typically get when you get a Windows instance on Amazon. So the difference is one comes with a full emulated environment. It is one for Windows. The other one comes with a para-virtualized interfaces. It's one for Linux. They both have pros and cons. So on ARM, we only have one type of guest that we think is actually the best of both. So it exploits the hardware as much as possible, like HVM guest. It doesn't require invasive modification in the guest kernel like HVM guest. So it's very, very easy to port an operating system to Xenon ARM. As a matter of fact, a colleague of mine ported FreeBSD to Xenon ARM in a couple of weekends on his spare time. And also, we exploit para-virtualized interfaces as early as possible in the boot sequence. That is good for performances and security. So overall, turned out the new Xenon ARM architecture is a very good match for ARM virtualization extensions, and a clean architecture means a smaller code base. So we managed to complete the port with far fewer lines of code than Xenon x86, as I'll show you in just a second. So I'm not going to get into any details, but basically this is how the Xen matches the ARM architecture. So Xen runs entirely and only in hypervisor mode, also called EL2. An instruction that was introduced by ARM with the virtualization extension that is called HVC is used for Xen hypercalls. And virtualization support in the timers, in the interrupt controller, and in the MMU are all used by Xen to export memory, time, and interrupt into guests. There's a very good match between the two. And this is the result. ARM v7 32-bit and ARM v8 64-bit support in the Xen hypervisor together amount to 1/6 of the code of x86 64-bit supporting Xen. 1/6, still providing a similar level of features. Obviously, a smaller code base is far better because it is less bugs, easier to make secure, certify, and so on. Right, so the port to ARM started at the end of 2011. We already achieved several important milestones, including having Xen support for ARM v7 in Linux upstream, Xen support for ARM v8 in Linux upstream. We also made 2 releases of Xen with ARM support, ARM v7 and ARM v8 support. And we're about to make a 3rd release. Most importantly, actually, the Xen project has been very successful in the last year or two. So look at the graph on the left. That's the amount of traffic on the list is steadily increasing. And we are at the highest ever level of individual contributors to the Xen project. This is in terms of the developer community, but let's see at the website and social media, we're up by 30% and 50% respectively. In terms of press mention also this year, we are far better than last year. So I'm not saying that all of this is thanks to Xenon ARM, of course, but certainly Xenon ARM had a big impact on this success. And we account about 25 to 30% of the overall activities that you've seen before to ARM development. So why is so high? Well, there are so many companies that are already developing, evaluating, testing, debugging, or just helping on Xenon ARM development. Not all of them, of course, they do ARM servers. Some of them actually work in very, in other markets, such as smartphone or embedded or set-top boxes, automotive is a popular one, but also more esoteric markets such as Internet of Things. So I've seen a demo of a flying drone running Xen, for example, or the aviation industry. So there are people certifying Xen for your plane, actual plane, bringing people around. So think about that next time you take a flight. We'll see. So all of these activity, of course, benefit Xen as a whole and ARM servers, of course, because, well, to certify Xen for the aviation industry, for example, you have to go through very, very thorough reviews. Overall, the code is going to be far better afterwards. Or if you need to run Xen on a drone, you actually need to be very responsive, otherwise your drone is going to hit a tree, right, instead of flying past it, right? So all these things means actually better software for everybody. So in terms of releases, we released first 4.4 at the beginning of the year, and we already support all the most important features. So this is also, like Kiko and John said, this is one I wanted to communicate, that in terms of feature, all the most important ones, the one you're going to be looking for, they're already there. So we do support 64-bit guest. We do support all the basic lifecycle operations on creating VM, destroying VM, rebooting VM, pausing VM is all supported. But we go farther than that. We support on ARM v7 and v8, we support memory ballooning, so increasing and decreasing the amount of memory of a VM at runtime. We support all the different various scheduler configurations. On Xen, different from Linux, come with several different schedulers by default. Some of them are real-time schedulers. So you can pick whatever scheduler you like. They're all supported on ARM. Some of them, again, are real-time. You can pin vCPU to physical CPUs. You can split the physical CPU into pools and run different schedulers in different pools. All of this is supported in 4.4. Linux is already capable of booting ASDOM 0 or ASDOM U, 32-bit or 64-bit with SMP support on Xen. All the paravirtualized driver in Linux, front-end and back-end, have already been enabled on ARM. So as you can see, we are quite far down the road in terms of support. There are lots and lots of features coming in the next release. We are about to feature freeze in 2 weeks from now, actually. I'm not going to go through all of them, but there are many, many improvements. More than usual, actually. The activity has been very hectic in the last 6 months. Interrupt handling improvement, memory handling improvement, new drivers, and more. But what I wanted really to show you is some benchmarks, because well, we already showed demo in the past, showing the Xen in small demo clouds with orchestration software running on top of it. I mean, the software is basically ready, but how stable is it, right? How performant is it? So this is what I want to answer here. And also, I ran this benchmark to just know the answer myself. Okay. So I wanted to know whether the new architecture actually proved to be correct, proved to be as good as we thought it was. So to do that, I wanted to compare the overhead of running a workload, a benchmark, on a VM compared to native, and do the same on different architecture, on x86, and on different hypervisor, on Xen and KVM. So the idea is to find out how much is the hypervisor tax of running this benchmark inside the VM compared to native, with the same number of physical CPU and virtual CPU, the same amount of memory. So 0 overhead means this benchmark runs just as fast inside your VM as on native. Is the best possible outcome you can have. So running it on a VM, it doesn't slow you down at all. 2%, it means it's 2% slower. It takes 2% more time to complete the benchmark inside the VM compared to native. So on the ARM side, I've used an Apply Micro Xen that is an 8-core SoC, ARM v8. And on the Intel side, an Intel Xeon x86-64, 2 sockets, 6-core per socket from a couple of years ago. So, the first benchmark I use is Kernbench. It is a time to compile the Linux kernel. So as you can see, Xen on ARM here are basically 0 overhead. Xen on x86 is about 2%. KVM on ARM is about 3%. KVM on x86 is about 7%. So Xen in general has a lower overhead than KVM, and Xen on ARM beats even Xen on x86 that is 10 years older. These are really good results, but Kernbench is a strange benchmark because it's a time to compile the Linux kernel. Obviously, the Linux kernel compiles very differently on ARM and on x86, so maybe this result is not very meaningful. So let's see another benchmark. This is the PBzip2 is a parallel bzip2 implementation, and this is the time to compress a 4 GB movie in bzip2 format. So Xen on ARM, again, has almost less than 1% overhead. Xen on x86, about 3. KVM on ARM is about 4, and KVM on x86 about 9. So it's exactly the same figures as before, more or less. Next, I went to run FIO, that is disk I/O benchmarking suite. I ran a random read write benchmark. So in this case, Xen on x86 is the one with the lowest overhead, and is basically 0. Xen on ARM still does very good. I think it's 1%. KVM on ARM, not as good, 8%. KVM on x86, about 2. So still, Xen on ARM has pretty acceptable performance on disk. And finally, SpecJBV. So this result is a bit surprising. So as you can see, still Xen on ARM has a lower overhead than KVM on ARM, and Xen on x86 has a lower overhead than KVM on x86. But the difference between the two architectures is really high. And honestly, it's higher than I was expecting. So I ran this benchmark more than once, but these are the numbers. And actually, I tried to find out an explanation, and the main reason is the kernel that I use for this benchmark, that is the 315 RC8 on Linux, release candidate, is lower than usual running on x86 VMs, at least for this specific benchmark. So on 313, the overhead will be significant. Still, x86 will have a higher overhead than ARM, but not as high as 6% and 9%. Is a bit too high. It would be about 3, 4, and 6, 7%. But still, ARM is doing very well here. The last one is a benchmark that I haven't run. It takes several hours to run. This also testifies how stable is the platform and this backend, because it's actually a collection of integers crunching numbers benchmarks. It takes really long time to run on x86 too. So Apply Micro runs this benchmark, and the overhead is 2%. That is still a really good result, so I can tell you that. So this is the end. Why use Xen on your ARM servers? Because Xen is already very strong in the cloud, has a very healthy and strong community, using the hypervisor in several different markets, as already successful actually in segments such as automotive and embedded. Xen gives you the strongest security guarantees among all hypervisors. Is a preferred platform for the 3-letter agencies of the United States government, and has an excellent security track record. And it's easy to deploy from source, but also is available on many Linux distros. And finally, as you can see from this benchmark, has a really minimal overhead. So really, if the price is so low, why shouldn't you run actually Xen on your ARM servers? So yes, we have a lot of documentation, an active mailing list, white papers to describe the architecture. So feel free to engage with the community. And I'll take any questions.
So what are your thoughts on platform device pass-through to guest VMs, which are non-PCI devices? Let's say I have a bunch of 10 gig NICs. Are you only talking about paravirtualization, or are you looking at some generic frameworks like VFIO platform? So
VFIO is not using Xen. We have a different way of assigning devices, also because the kind of resource management that VFIO does and the interface that VFIO does is for user space, while for us the hypervisor is one level below. In any case, we have device assignment for non-PCI devices. All the core technology is there in the next release. 4.5 is one of the new features. We are looking at ways of exporting to users. It's not as easy as a PCI device where you say, I want this PDF to this VM. So what we're looking at right now, and what we will surely have, is a way to specify an interrupt number and an MMIO region, and you can say, I want this and this guest. And this is the way it is used today in automotive. So the automotive guys, what they do is they, for example, want an automotive, an Android VM with a graphic card, and they use this trick to assign the graphic card to the guest, and then they want another VM with all the high reliable services, and so yeah, so it's already there, basically. It lack of a very polished, simple to use interface to non-technical users, but the basic technology is ready. All right.
Okay. Thank you, Stefano.
Thank you.
Interesting.